eigenvalue extraction with quite a few parameters here having to do with the eigenvalue and the eigenvectors. Below here I've got the data entry for our matrices, starting with the rod stiffness. Next I enter the stiffness of the actuator, which is only one column. Then I have the mass of the rod with its bookkeeping entry and then the columns. Here's my complex eigenvalue solver using this Hessian approach for complex eigenvalues. Results are printed out as shown below here, and here's a echo of the matrix for the mass of the rod. Next I output the system stiffness, shown here. The place where the 3 value for the actuator stiffness enters is here, which would be the upper right corner, and that contrasts to just the rod stiffness, which is here. And when I say rod, I mean fishing rod, not a rod element. It's really a bar element. Well, the results that we get out are shown below for the eigenvalues, and it gives the imaginary parts here, and then it gives the real part to the left here. So this is the frequency of each of the 3 roots, and this is the envelope, which is 0, means that it's neutrally damped. Let's look at the eigenvectors for this problem, remembering that they are a function of the robotic stiffness to the fishing rod stiffness ratio. We've done some calculations for that ratio that we've called pi 3 equal to 3.0. Here are the tabular results, and below are shown the 3 eigenvectors in the problem. One might have expected there to have been perhaps 1 nodal crossing here, 2 here, and 3 here. We seem to be getting, in fact, counting the left 0 crossing, 2, 2, and 3, and so you might wonder what's going on here. But let me explain that this first eigenvector derives from the rigid body rotation of that fishing rod when the robotic stiffness is turned off. And so this would have been a mode in its purest form without robotics intervening as a pure straight line here. So that helps you understand the 0 crossing effects a little bit better. Let's show a figure of oscillation frequency for the robot arm as a function of the actuator stiffness. We did a calculation in detail showing these 3 solutions for frequency. All of those had 0 real parts, which meant you had undamped oscillations. If we continue that study and try different values for this actuator stiffness, perhaps 2 and then 4 and so on, we find that these 2 branches of the frequency curve coalesce. And we find that the branch above that coalescence is actually unstable, with one branch or one of the frequencies having positive real part on the frequency and the other one having negative. So you get one unstable root then in this problem. So we have Flutter up there. So we've got the interesting case where we have down below this point we have stable solutions, and up above we have unstable. The instability is strange in a way because when you get above 20 values here on actuator stiffness, then you get divergence, a static divergence. That means that if we were to turn the robot on with values roughly between 4 and 20, it would oscillate and beat itself to death. If you turn it on and it had an actuator ratio, stiffness ratio above 20, it would monotonically slew in a big circle and clobber whoever was nearby in just one swing. The branch shown here for the third frequency is neutrally stable at all times. So this chart is not at all unusual to find in Flutter problems in aeronautics. In fact, I'm familiar with a curve exactly like this from panel flutter at supersonic flow, and wing flutter at both sub and supersonic flow is similar. If you add damping in the problem, you can sometimes delay the onset of flutter slightly above this coalescence point and get some slight benefit. But damping is generally not very successful in preventing this kind of coupled mode flutter. Let me summarize some of those results that I mentioned verbally in the previous figure. The robot fisherman goes berserk at this stiffness ratio greater than 4, and that's with no damping. Damping would probably delay the onset of the instability. It's a coupled mode type of flutter when two frequencies coalesce. The robot fisherman has a static instability at stiffness ratios greater than 20. And lastly, we've arrived at this paradox that to have better position accuracy, we'd like to increase the gain. On the other hand, that degrades the stability. And this is often the case. So you have to pick some intermediate value that you can live with. We would have to put our robot fisherman out on the bank with a actuator stiffness gain ratio at less than 4, possibly 3 with some margin for safety in terms of stability. Well, it's time for a problem session. Let's start out with a non-conservative problem here. This is a planar truss with a single live load over here shown in red. And what we'd like to do is minimize the displacement response out here at U6. It's going to exert a force proportional to U6 but opposite in sense, and it's going to apply that force here, sort of at the wrong point, you might say. So this is a non-collocated system. And the fact that you're sensing the displacement here and opposing it over here is the problem. The live load was clear over here. So this is interesting. We're going to assume that this F4 value is reacted against the ground. So we could either show it bumping against some firm ceiling up here, or we could ground it down in the other direction if we wish. Let's show the relevant equations for this system, and then let's characterize the system. We'll model this system with discrete truss elements. We'll remove the degrees of freedom at the ground because those degrees of freedom are actually constrained. That leaves us 6 analysis degrees of freedom at the top of the truss system, U1 through U6. I'm just using general terms for the stiffness and mass coefficients. The actuator force acts on U6 as shown, opposing its displacement. We can absorb that actuator force into the system stiffness matrix. We can identify what we think of as an actuator finite element, a fictitious element joining degrees of freedom 4 and 6. A little more conservative way to do the model, and probably preferred by some people, would be to show how the actuator is connected between that point on the truss and ground, say the ceiling up above, and creating temporarily a degree of freedom U7 there. That would be ultimately constrained and partitioned out, however. The actuator is non-collocated because the point at which you're sensing is not the point at which the corrective force is applied. And this could cause instabilities because of a non-symmetric stiffness matrix. Problems 2 and 3 in this session are really not non-conservative problems. It's the last two problems in the course, and I wanted to add them before forgetting these and get them documented. They're interesting problems, so I think it's important to go through this. They logically could have been added, though, to the previous lecture on just active nodes, but let's do these for the fun of it and close out our lecture series. Problem 2 is on the robot screwdriver. I thought about trying to drive a screw into a wall, and usually the arm here would be the human's arm and the actuator would be some sort of power-driven screwdriver. In order to turn this into a completely mechanical system, let's presume that the left wall here is rigid. The elasticity of perhaps a human's arm is represented by a torsional spring here. The elasticity of the actuator out to the screwdriver blade is a second torsional spring. And then the screw, as it goes into the wall, we'll consider by a very simple model as a torsional spring as well. So there's another spring in here, which is then fixed in the wall at the right end. So I'm trying to turn this into something that we can model. Now the actuator is trying to drive the screw by reacting against this rigid wall on the left. What you'll find is, though, that because of the enormous back reaction and torque of the screw on the wall, that this elastic arm here is going to rotate some and prevent the actuator from reaching the desired static location of the screw head. I'm saying this because we'll have the actuator sense the angle between the screwdriver blade U3, which is at this location, and the end of the arm U2. So we won't let it sense how much elastic motion there is in this arm, which degrades the static position. The torque the screwdriver applies will be proportionate then to that perceived angle that it thinks it has rotated compared with some command angle. The model of the screw going into the wall is a very simple one, so I'm doing some physical modeling here. I did this because of some actual practice, whereas you really tighten a screw into something like a hardwood, like oak, and you've under-drilled your hole, it really can get harder and harder to drive that as you turn the screw. And so I just presumed a linear law here that the force required, and it's a torque in this case, to turn the screw is proportionate to the screwdriver blade angle. And I've chosen this coefficient. So suppose the robot is commanded to turn the screw 0 to 90 degrees as the instrument itself senses. Then the question is, what is the actual angle that the screw is turned, considering that there's some degradation of the position by the elastic arm? Okay, so in our solution, we're going to consider the connection between the screwdriver blade and the screw head to be rigid, and then we will try to solve for the angle U3, which will give us a measure of how close we have come to 90 degrees. That is an absolute angle since the wall is fixed, and so that will be how far the screw has turned. Now let's assemble the equation of equilibrium. This is a static problem, so we don't get into inertial and damping effects. The actuator forces are shown here, and you have to get the signs right on these. The one is the live moment applied to the screw, and the other one is the reaction moment against the elastic rod. The rod itself is modeled here, which is just a small torsional element. The screw is modeled as a small torsional element, and now we can assemble, putting those actuator forces in the proper places on the right-hand side for these two components, F2 and F3. The equation of equilibrium is shown here as we've brought in the actuator moments. This is a static equation of equilibrium rather than an equation of motion because we've not posed it as a dynamics problem. When we put in the proper numbers over here for the command angle of pi over 2, then we get a completely numerical problem. We've moved the homogeneous stiffness terms to the left that have to do with the actuator moments. We partition out the second and third equations because U1 and U4 have been constrained to 0. We can solve for those reaction moments, F1 and F4, later if we so desire. The reduced set of equations is shown below, and those are simply solved by Cramer's rule in the next figure. Cramer's rule uses the ratio of two determinants. Since we're interested in the variable U3, which is the rotation of the screw head, we substitute the force vector here into the second of the column vectors in this matrix of coefficients here. And we get the answer 81.1 degrees. We were asked to drive that screw in 90 degrees and only reached a fraction of that, so we're about 9 degrees short of our goal. That's due to sensing of a relative angle rather than an absolute angle at the screw head, and the reason those are different is due to the rod elasticity. Our last problem is an actively controlled shock absorber for an airplane. These kinds of active controls are going to become more and more common. I think we will have this in automobiles as a common feature in not too distant a future. I want to consider how an airplane might bounce upon landing and how the shock absorber might be used to reduce that kind of bounce. Many of us are aware of that when we land on commercial airplanes. We'll have the mass of the airplane viewed as a point mass, and then some elasticity, so that's a sprung mass here between the airplane and the upper end of the shock absorber proper. Then the shock absorber, which I'm viewing as an active joint, will be this cloud-like structure, which will have another node. So it's the spring going across here, and I sketch that in the next figure along with a dash pot for its damping character. Then from this node, let's lump that all the way to ground so that we can connect to ground, and there would be a certain springiness involved there. A lot of that would be in the tire itself. The idea is that we would give the aircraft a certain downward velocity with the bottom of the wheel fixed, and then watch and see what happens from that point on. I'm only interested in developing the equations of motion here, otherwise we'd have to do some lengthy computation and develop the physics of this. We're going to neglect the mass of the landing gear and eliminate any unnecessary degrees of freedom. So we have the mass of the aircraft up at this node, which is by far the dominant mass in the system. It's the gap between nodes 2 and 3 that is the shock absorbing part of the landing gear. And then U4 will be in contact with the ground at a zero displacement for all times. Here I give some of the parameters of the problem in metric form, and here I give some of the stiffnesses of the system. Let's assemble our equations of motion. These are relatively placid in that the stiffness matrix is symmetric, so we don't have circulatory forces. We do have a damping matrix which can absorb energy. The mass of the airplane itself dominates the inertia effects, and we neglect other masses. Here we have the damping effect of the actively controlled shock absorber, and then we have the stiffnesses of the actuator in the stiffness term here. Over here are the command values for the live control system. Our last step is to partition out the degree of freedom at the ground because it's constrained to be 0 at all times. So we don't really discard it. We could use it later to find the reaction force at the ground, but we set it aside. That would be a nice way to put it. And then putting in all the numerical values, these are the equations of motion for the system. And we can integrate those numerically for any set of initial conditions that we'd like, using perhaps the Newmark beta approach.